terrible path that we had to follow trying to go to the representation theorem, to the definition of a moment tensor, to the definition of a seismic moment, and to the final step, that is the vision of a double couple representing a shear dislocation on a fault. Okay, and so this is the picture that is really what we need, because actually the problem is that we have an elastic body of a given volume V surrounded by a surface that could be the surface of the Earth, with an additional surface that here is called sigma, that is made by sigma minus and plus, so the two sides of the blocks that are defining sigma, over which we have a shear dislocation. What does it mean? Discontinuity in the displacement field, not in the tractions that are continuous along sigma, and that we cannot treat directly, so we're looking for something that is representing this. That's the representation theorem. What we have used till now are, well, some theorems, uniqueness, reciprocity, and the definition of the Green's function with the equations of elastic motion. Equations of elastic motion that for the Green's function are not homogeneous, in the sense they are not equal to zero, they are equal to something that is a delta. But please do remember that delta for the elastodynamics problem is a complicated delta, because we have a delta in x, the location of the force, a delta in t, and that is fine. Maybe you can put the source in 0, the time starting from t equals 0, okay, that's fine. Plus what we called a delta in direction. So it's a delta that is not made by depending upon one variable, but 3 plus 1 plus direction. And we defined it. We defined it in a polite way because, okay, if some boundary conditions, like for example, the surface S is a free surface, so G, the Green's function, is a tensor, it's symmetric, and if we assume some homogeneous boundary conditions on the body, like on sigma, free surface, okay, it's well defined inside this domain. Well defined. We still have to find it, but we defined it. So we used it, and we coupled it, we used it inside the reciprocity theorem, and then we obtained an expression for the displacement in this body, and what we're looking for is a vector. If you want, it's a vector with 3 components, n, that is a function of x and t. This is what we are looking for. Displacement in a body with a volume V defined by its properties, surrounded by a surface S, where we have a shear dislocation. Okay, this is what we have been doing on Friday. And the result that we got was something like that. Yeah, I know, it's terrible. So, trying to avoid the complications coming from the inner dependencies of these quantities here, the representation theorem is saying, okay, the displacement u at a given position and at a given time t in our body is due to body forces, like gravity, for example, that are acting somewhere, and of course you have to convolve them by the Green's function, it's by definition. But wait a second, because we will neglect this part, okay? It will be out of the game. Plus some additional terms. Due to what? Well, due to the elastic forces inside the body. What are the elastic forces? Well, they are embedded in two quantities. that are related to the discontinuities that could be present inside the body, like traction discontinuity or displacement discontinuity, over some surface that for us is a fault. Okay, if we consider traction discontinuities here, then we will have to convolve them by the Green's function. But we will not use that, because we will assume that we have a pure shear dislocation. So also this term here is going away. What we are left, and this is what we have to use, is this. What it's telling is that, okay, if we have displacement discontinuities of a fault, we have to take into consideration their amount, the direction of the normal of a fault, that is just a geometrical term telling how the surface sigma is oriented in space. And if it is a plane, it will be just one direction. Okay? It's the normal to the fault. Here we have the medium properties. Up to now, that is the most general that we can imagine. It's nothing else than the Hooke's law generalized, telling us the elastic properties of the material. If it is homogeneous, it will contain just lambda mu. But again, if we assume that the discontinuity is related just to pure shear dislocation, we will see that the lambda will not enter into the game, and just mu will be there. Then, that term, that is our source, has to be convolved by the spatial derivative, that it is here, of the Green's function of a medium. Now, let's try to use intuition. The Green's function is the component of displacement n due to a force pointing in P, by definition. Okay? So we have a force acting in P, and when you take the spatial derivative along Q, actually you're creating an arm in the Q direction. So that's a sort of a couple. Okay? Spatial derivative is of a force is creating a couple. So, in very simple terms, this is nothing else than a set of couples distributed over the fault with arm in Q and with a force that is related to the amplitude of a slip in that point. And please do remember that this is an integral over the discontinuity, so over the fault. Now, if you want to call this really a representational theorem, you can imagine to write that term, that is the only one that we're looking for, into a different version so that this term here can be written like this. If we can do that, then that expression will be a force representing this. Okay, and the answer, after some algebra, is this. I hope it's going to appear. We can write the displacement inside the body, the Earth, at a given point x in time t as an integral over the volume of the Green's function convolved by a representing force that is this. If you want, that's the final statement of the representation theorem. It's not the most useful, because the most useful will appear in the next slide. But what it is telling us is that sorry, it's not your fault, it's my fault. So what it is telling us, and now we have a fault, is that if we take our elastic body with a surface sigma, where we have a displacement discontinuity, what we can do is to remove it and to place there a set of equivalent forces. Okay? So no more default, no more shear dislocation, a set of equivalent forces. These equivalent forces can be imagined like this. So we have a delta with an arm in Q acting in P, because that's the P, and so arm, force. What about the amplitude of this force here? Well, it's related to the amount of slip in that point times mu with a geometrical information, because knee could be like that if it is a plane. It's telling you where the fault is and how it is oriented. If you have a strange fault, then knee will be changing. It will be normal in each point. Okay? But for a plane, it's just a direction. And if you think about it, a unitary vector that is telling us a direction is nothing else than a couple of angles, strike and dip. Okay. So, representation theory. If you have an elastic body, a volume V, with a surface S, and a fault over which we have a pure shear dislocation, we can write the displacement in this way, where we have a Green's function convolved by an equivalent body force that is made like that. You could ask, okay, why all this mess here? Why we don't consider the fault? Because we can solve this problem. Okay? And this is what we will have to do over the next lecture, and maybe starting today. Okay, as I told you, let's try now to rewrite that expression in some different fashions that can be useful for us. By the way, that's the most useful and powerful expression that we can use to model seismograms. So it's the key tool to do many things. For example, to compute the displacement due to a model of a fault in a given model of a medium, and to compare with observations and try to invert for something. So direct for inversion. It's the basic tool to compute synthetic seismograms with different methods. The different methods will change according to how to find G. That's the next problem, not for today. And maybe we can use it to write it in different ways for following some approximations. And what we're going to do, and we started to do it at the end of Friday's lecture, will be a model that is very simple, that is a point source. Right, that one, is it a point? No, if we stay here, it's not a point. But if we move for, 1 kilometer, it could be considered a point. Okay, so that's the summary. As I told you, we can imagine this as a set of couples with different directions, forces acting on P, arm in Q, and the strength is related to U, actually mu, and so now we're getting a vision of what will be the moment tensor at the seismic moment, and it's following a distribution on the fault. Okay. As you can see here, this is a tensor, because if you change P and Q, X, Y, Z, 1, 2, 3, you will get 9 quantities. Remember the convention of the repeated index summation here. So you see here PQ, PQ. This will be simplified in the example that we will do today. Then the quantity here, N, will depend on the Green's function, N. Now let's define a quantity. Let's call it density of a moment tensor, like this, and we can write it like that. You see, it's getting simpler and simpler. Okay. Next, let's give a look to MPQ now for an isotropic medium. Because the representation theorem in the version of Baric and Nopov was for a very general medium, also anisotropic. But let's imagine it's isotropic, then the mass in Ci, will be just going into lambda mu. So if you give a look to the definition of MPQ, for an isotropic solid you have two versions. Full, but wait a second. If we are considering a pure shear dislocation, the slip on the fold will always be orthogonal to the normal of the fold. So this, that is a scalar product, will be always zero if ni is orthogonal to u. Okay? And what we're left is this. So just mu and something that is telling us where the dislocation is occurring, how much it is, and the direction of a normal of a fold. Okay. Final step. Let's imagine to be so far from the source here, but we can imagine that it is a point. So now let's perform this integral. If we perform this integral, and you imagine that all the contributions for the different points on the fold actually are just one, we can average it, and we can compute this integral here. It's an integral over the whole area of the fold. Okay, let's define it as a tensor PQ, PQ. So it has 9 components, but actually, since it's defined like that, it's symmetric. So we can diagonalize it. We can use the trace of a diagonal tensor. It will be an invariant. We can look for eigenvalues, just 3, and we will see now a specific condition. Just 1 second. So let's define it. Let's put it here, and then all the terrible expression that we've been starting from, it's becoming very simple. This is called moment tensor, second order, symmetric, PQ, PQ, and N. And now we'll give a look to it, please.
How can we isolate the derivative of G from surface, from discontinuity surface? Because derivative of G is also inside the integration of discontinuity surface, yeah? No.
I'm not getting it, sorry, let me go to the next one.
Yeah, in that slide.
Okay.
Derivative of G is also inside the integration of discontinuity surface.
Wait a second. If I get your point, and it is a good point, remember that displacement is discontinuous here, but not the Green's function. So the Green's function is continuous everywhere in the medium. So the derivative, I think you're referring to this one, okay, is applied to a quantity that has no discontinuities inside the body, because the Green's function is politely defined. You can demonstrate that G is well defined if you apply the boundary conditions on the body. Like, for example, this is a free surface. G is defined and it is continuous across the fold. G. This is discontinuous. Actually, that's the difference between the displacement on this side and on this side. So it's very shear dislocation. Okay?
So, what is the last slide?
Oh.
is minus? But it's confused, sorry.
Oh, because actually,
So the next slide, there's no minus again.
but there is no more F.
Okay. But something that looks like F.
But look, that minus is coming from this definition actually.
Okay.
Just trying to represent this as an F.
Okay.
Now remember, we're getting out from this and we're writing this as an F.
Okay.
So the minus is coming from the representation of that point by this.
Okay.
Okay?
Okay.
The minus is related to the derivative, actually. But remember, here, no derivative. Here we have a derivative. Okay?
Okay.
Thank you. Now, this is the most important expression of the whole course. It's the basic tool for whatever modeling you're going to do. Yes?
The first time new u, we always is or will be zero if u and new are different.
Now, are you referring to this one?
Yeah.
Look, whenever ni, let's imagine it's the fold, okay? And we will see an example today. Ni is defined, right? It's constant, it's a plane, okay? Now let's consider the dislocation on the fold. If, and only if, the dislocation is on the fold, wherever but on the fold, they will be always orthogonal. As soon as the slip is also containing an opening, it will not be zero, and lambda will play its role. But if you assume that there is no opening on the fold, that will be always zero. So, to answer, whenever you're considering a pure tectonic earthquake with no explosive or implosive component, it's zero. But there is room for openings also if you consider it zero. And this is what I'm going to tell you in one second, I hope. I don't know if I answered to you. What I'm trying to say is, okay, you're not forced to consider it zero. But if these two vectors are orthogonal, it's zero, because it's a scalar product. If u is like that, no, it's no more zero. And lambda will be there. Okay? If not, lambda is out, and we are left with a pure symmetric tensor with just mu. Remember that this is going to be used only when we use a pure point source. Because this step here is considering a point as a radiator. And you should ask, when can we apply this condition? And this condition here is called far source. Okay? Far source condition means that we can approximate the source as a point. Now you should ask, how much far? That's a good point. Usually, if the largest dimension of a fold is L, typically its length, let's say that the distance should be much larger than L. Okay? This is far source condition, and it means that we are considering the source as a point. Okay. Now, and this is moment tensor. And please do remember, well, we will see it now. Okay. Now a slide that is containing a lot of information that we will be used. Again, moment tensor is symmetric. And the roles of u and ni can be changed. It's symmetric, right? So we will never know which one is U, which one is Ni, just using the radiation. You can change that. It's symmetric, right? Okay, this will reflect when we're going to discuss the focal mechanisms, but we will never be sure which one is U and which one is Ni, or vice versa, just looking at the pure radiation. And this is called the fault auxiliary planes ambiguity, just related to its symmetry. Okay, let's remember, it's symmetric. Then, what about LPQ? Well, it's symmetric, so it can be diagonalized, and we can write it using the three eigenvalues, right? If we use the principal axis, a symmetric tensor will be diagonal. Let's order them according to their magnitude. Let's compute the trace, so their sum, it will be invariant, and let's make an average. Okay, this part is called isotropic. Wait a second, because if we consider internal sources and not external forces like a meteorite impacting on the Earth, that's external. But if it is internal, the sum of the forces has to be conserved, so the trace has to be zero, because it's a sort of a sum of all the sources. And what we are left is what is called the deviatoric part. So we compute this, we divide it by 3, these are 3, and this is what is left. Wait a second, because if the source is internal, not only the forces have to be zero, but also the total moments have to be zero. So, actually, when we consider a point source, internal source, okay, the trace has to be zero, and one of them has to be zero. Why? Because the other ones have to be some plus and some minus, and the sum has to be zero. So, the end of the story is that if you consider a pure shear dislocation event related to an internal source, and you can consider it as a point, all the tremendous complications are just ending into this. Everything is zero, plus m0, minus m0, and you should ask, what is m0? Okay, let's remember the definition of MPQ, and it's integral. It's just the average, the integral, over the fault of mu, times the average slip on the fault, times the area of the fault. There you go. And that is called seismic moment, and these dimensions are force over an area times a displacement, so it's a moment. Newton times meter, dyna centimeters. Yes?
Okay, some of the diagonal elements can also be zero by other ways. So why this way?
Because we are considering a pure shear dislocation.
When you say pure shear dislocation,
Again, a dislocation means a discontinuity in displacement on a surface, okay? And the direction of the dislocation is always perpendicular to the normal of a surface. What I'm trying to say is that you have to move your hands without making openings. That's a pure shear dislocation. Pure shear means that only mu is there, otherwise you have lambda. So, to have total forces zero, the trace has to be zero. To have all the moments zero, the only possibility is that when you have a point source, that you have a plus couple say plus and minus, and one has to be 0. Otherwise, you're not satisfying the condition of null moment. For null resultant, the trace is 0. Okay? So this is related to the definition of the most important single quantity that we can imagine to describe a seismic source, pure shear dislocation seismic source, and this is called seismic moment. This is called seismic moment tensor, actually moment tensor. Remember, the tensor can be written in this easy way only when you are in the diagonal principal system. Otherwise, the off-diagonal terms, they can be different than 0. But to preserve total trace, the trace has to be 0, and one of the principal eigenvalues, one of the eigenvalues has to be 0. In general, how the moment tensor is made? Well, just by definition, it's a set of couples. It has two indexes. So please remember M, P, Q. What are the physical meanings of P and Q? P is the direction of a force, Q is the direction of an arm. Together, they create a couple. So 1, 1 is a force pointing in 1, and the arm in 1. So it's a dipole. 2, 2 the same, but in the other direction. 3, 3 the same, but in the other direction. Now give a look to this. If you put them all together, that is the trace, it's something that could be an explosion if it is positive, or an implosion if it is negative. If it is 0, no implosion, no explosion. What about the diagonal terms? Let's give a look to 1, 2, for example. Means the force is pointing in 1, and the arm is in 2. It's a couple. 1, 3, 1, 1, 3, and so on. So remember, it's a second order tensor, symmetric, and it's expressing a set of couples. I hope that in some slides, we still have some terrible slides now, but the last part is totally devoted to a specific example. So I hope that discussing that example, some hidden features here will be revealed. So maybe let's wait for the next slides. Just as a sum up, the representation theorem at its end, when we consider a point source, it's telling us, okay, you can get out all the complications of the fault, and what you have to do is to replace it with a double couple. That is made by two couples, and each couple has a moment plus m0, minus m0, the total is 0. The total resultant is 0, and you should ask me, okay, but this double couple that is not in the Earth, it's a representative of a fault. Okay, we understand that its strength is related to m0. What about the directions? You should ask. What about, okay, should we orient it? Okay, what is going to decide the direction of F and the arms? Well, U and Ni that were on the fault. So the direction of U and the direction of Ni are telling us how to orient the double couple. So if the fault is like that, or whatever, Ni is telling us, right? The orientation of the fault, right? What is the orientation of the average dislocation of the fault? U will tell us. average U. So those two vectors, in some way, they are mapped in the orientation of a double cup. Okay? And now you should ask, how? Yes,
On the previous slide,
but if we continue like that, we will never finish this lecture.
yeah, I see how for the first figure,
This one?
yeah,
Yeah.
all are in one axis.
Let me call it X, Y, and Z. Okay?
Yeah. for the-
MXX. What does it mean? Okay, direction of the forces is in X. And the arm, I don't know, I don't have another chalk here with different color. That's F. And the arm is in X. Okay?
Yeah, but for
The other ones.
For the second one, I'm not seeing.
No, because it's not evident the picture maybe. Let's take MYX. Do you like it?
Yeah.
Okay, the force is in Y and the arm is in X. What does it mean? The arm now is here and the forces are like that. I'm sorry, I'm not a good painter. Do you want to take MXZ? Forces are in X and the arm is in Z. Just a couple, like that. I cannot do better. The arm is here. Here the arm is here, in 2.
Distance from between the 2 points.
Try to use your 3D imagination here. The arm is here. Here the arm is here. One index is telling you the direction of the forces. The second is telling you the direction of the arm. You see here? X, Y, Z, the second. Okay? So you have been asking, how? Some algebra. But I don't want that we are going to be confused by algebra, but just let's use logic. Now we have, and that's the final difficult part before the exam. The best physical vision of a dislocation of a fault, shear dislocation, is to consider the fault as a plane, and this plane is described by one vector. This is ni, right? The second average vector is telling us in which direction the dislocation is occurring, and that's the second. Ni and u, two vectors, right? Okay. After the representation, we have discovered NPQ. So it's a set of 9 couples that, according to u and ni, will tell us the representation of u and ni. So we have u and ni couple NPQ. We have a third vision that is intermediate, because when we go to NPQ, we know that it is symmetric. If it is symmetric, it can be diagonalized. What does it mean? That we can find a set of principal axes, 3, in which the tensor is pure diagonal, right? And we have used it in the previous slide. Okay. The set of 3 vectors that is the principal system for NPQ is called principal axis system. Thank you, of course, by definition. They are named TPB. You can do it on a paper. You have a symmetric tensor, and the problem is you can do it much better than me. Okay, find the principal axis. So let's diagonalize it, okay? It's a math problem. Good. Adopting that system, NPQ becomes plus M0 minus M0, 0. Okay?
Okay, that means finding the eigenvectors.
Yes,
Okay.
yes. As we did it for strength, for strength. Yes, yes. The eigenvectors are called principal axes in this case. And these principal axes are called T, P, B. Now, B is the axis related to the 0 eigenvalue. T is the positive, it just names, and P the negative. Good. How they can be related to U and N? Very easy. Because T will be with plus, P with minus, and B the vector product of N and U. And vice versa, you can find U and N by TPB. They are the same thing, just a different representation. Okay? Okay, these are called principal axes of a moment tensor.
You said B is the zero eigen value.
Okay?
Okay, but
B,
you said B is the cross product between me and me.
N and U. U.
You and V. Let's maybe call it U and V. So
Okay? Wait. You remember N and U?
yes.
Okay, B will be always perpendicular. It's cross product. Right?
Because I was thinking it's the cross product, and if they are orthogonal, then it's not going to be zero.
No, it's a direction. No, it's not 0. It's related to the 0 eigenvalue.
Okay, thank you. Related to the zero.
Principal axes are not the eigenvalues.
Okay.
The eigenvalues of a tensor are 3 numbers. In our case is M0 plus 0 minus M0. The principal axes are directions. One of the directions is this. The other one is this. Sorry, I don't have other. And the other one is in the other side. It's just a triplet. And if you use it, it is like that. Okay, in that system, MPQ becomes diagonal. It's by definition. How to find them? Well, it's related to the direction of U and N. It's just a different representation. These two systems are equivalent. Remember, for fault definition, we have just N and U. That's the physics, okay? The rest is math, okay? And the third terrible representation is, okay, given a fault, this is relaxing. What about the elements of MPQ when they are not in the diagonal system? In the diagonal system, we know plus, minus, 0, okay? But in general, how can they be written using U and V? That's the final step for conventions. It's just algebra, okay? So what do we have here? Well, wait a second. This is the fault. So we have an area with its normal, and its normal is related to strike and dip in geological terms. Are we okay with this? Ni is nothing else than strike and dip. And the slip vector. Okay. Remember the conventions for a fault in geological terms. The strike, the dip, and the rake. 3 angles. Okay. Now, that's the fault. With the representation theorem, we can throw away the fault and consider just a double couple, whose orientation should resemble the fault and the slip of the fault. And that's this representation. But this representation is also related to the principal axis. So if you have something like that, T, P, and B that is coming out from the screen are equivalent. this is equivalent to this, it's just the principal axis notation, and they are equivalent to that. Good. How to relate them? Well, it's just geometry. For example, and this is maybe a very important picture, but it's very simple. I try to modify the picture on the Stairway session book with our notation. So what do we have here? Well, that's the fault. Okay? The fault is defined by a strike angle and a dip angle, right?
Yes.
And phi and delta are nothing else than ni. Given ni, it's like giving this and this. It's a plane. I hope you do agree with me. It's geometry. Okay? What is left? The slip. Now, this is a vector. Remember, it's the average. We made an integration. Now, let's imagine this is the average slip. It's what I'm trying to do since 3 lectures, okay? Now, what about u, the slip on the fault? Well, it has a direction, and that's the third angle. This one, right? Okay. You can call it slip angle or rake in some geological terms, and that is an angle plus its amplitude. How much it is? 1 centimeter, 10 meters, okay? The amplitude of u. Okay? Good. Now, how to relate u and ni to these angles? Well, it's just geometry. We can always write them in terms of the amplitude of u and some sines and cosine of these 3 angles. What we have to do is nothing else than try to write this and this in terms of the other angles. It's geometry, okay? So we can write u and ni given the 3 angles and the amount of slip. That's geometry. Once we have u and ni, we can use a representation theorem. And so we can, wow, my God, write these elements here in terms of u and ni, and thus in terms of the angles and the amplitude of u. What is the amplitude of u? Here. Because remember that m0 is mu times the area times the average slip. It's there. So the final representation of the slip u on a fault defined by ni is this. And these are the elements that maybe some of you will apply in your future career when you're going to do inversion for double couple.
And where are mu and a? Because average of u is inside the modulus of u. Yeah.
Wait a second. We started from a fault. 3 angles plus the amplitude of u. Strike, dip, rake, amplitude of u. Is that fine? Okay. We can write u and ni instead of the angles and this. It's the same. U and ni where are inside the representation theorem. Do you remember? Good. So we start from this, we plug them inside the representation theorem, and so we have to use this expression. This, okay, do you remember? Amplitude of u, ni, mu, okay. We do the integral using u and ni with the definition. We end with MPQ. MPQ is containing this. So, you said, why mu? Because we use the definition of u and ni inside the representation theorem. And then we got this. So, just to tell you. So, we have been spending 2 hours just to go from the fault and the slip on the fault to these 6 quantities. Wait a second. No, wait a second now. Too many questions, I'm sorry. Otherwise we will never move.
Okay.
Once you diagonalize the 6 elements here, if you use TPB, they're just M0, 0, minus M0.
Okay.
So what I'm trying to tell you, okay, what about the orientation of a double cup? It depends on you and me. Just using those angles. So you use those angles, you find you and me, you plug them inside the representation theorem, and here you go. Because they are a function of the tip, the rake, and the strike. Definitely, at the oral exam, I will ask you every detail of this formula.
Just kidding.
And you can say whatever, because I don't remember. Okay? Okay? Now your question, but final.
Okay, it's just to want to clarify. Is this all these only for pure slip dislocation? And,
Pure shear dislocation on a fault that is treated as a point.
Okay.
Fasos.
Whenever you move from one of the assumptions, you have to go back in the representation theorem.
Okay.
Do you want to have some explosion? Oh, well, you have now to use MPQ with lambda. But you can also use, look, do you want to treat an explosion? Okay. You can always use MPQ without imposing that the trace is 0. Do you want to use, and this is what is going to occur, for example, if you are going to work in a volcanic area, you cannot use this condition. So you cannot use this condition. You have to relax it. Otherwise, your computer code will find solutions with a beautiful 0 there, but they will not be realistic. So every time that you relax one of the assumptions that we made, we have to go back. If the source is not a point, well, we have to use this. Okay? Okay. Let's try now to move and give a look to a specific example. These are the final slides about the representation theorem. My goodness. And they will start as a mess, as usual with my lectures, but the final slide should be easy. A particular case. So in our thriller, now we're going to look for a specific, how to say, no, I don't want to use violence, but so, okay, we're going to a specific, very specific case. The fault is strange, but the slip on the fault is occurring on a plane that is exactly this. So it's the plane X, Y. Okay? So it's something like that. Okay? Then we assume, let's imagine X, Y, Z. So the fault is at the plane Z equals 0, X, Y, and the displacement is occurring U into the X direction. Okay? It's just a specific case. And we will assume also that this fault here, whose strike is along this direction, is pointing exactly to north. Okay? It's just an assumption. Actually, it should be like there, but okay. I don't want to turn the table in different direction. Okay? Good. What we will use now are the different steps that we have done through the representation theorem to see how all the elements are going to be expressed. So, the fault lies in the plane Z equals 0. So, now me vector is very specific because it's 0, 0, 1. Is that fine? Okay? That's me.
It's always in the Z direction.
Yes. In this case, it's called Xi frame, okay? But it's Z. Pure shear dislocation, and it's going to be X direction. Okay? So U is there. Okay? Now, the general expressions of a body force equivalent that we found some slides ago, in general, they are like this. These are the general expressions. Question, okay, what they become when we consider this case here? Let's give it a look. Let's consider an isotropic medium. So, we have just lambda mu. Plus, we have a pure shear dislocation that is acting along x, okay? Only mu, and going in that direction. This means that all the terms of CIJPQ vanish because it's isotropic, pure shear dislocation, and so on. Just two are left. 1 free and free 1, with 1 free, the first two fixed, because remember, 1 and 3. Remember here?
Yes.
IJPQ, PQ, I, P. So I is along X, just 1. Ni here is J, is just 3. So these two are fixed now.
1 and 3.
And if they are fixed, by symmetry, the only two terms that do not vanish now are 1 free and free 1. Okay? And they are equal to mu. If you replace now, instead of CIJPQ, these two cases, here is what we are left with. Wait a second. What is telling us is that the representation theorem is saying, okay, guys, you can move out your fault with a slip, blah, 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 and now you can take two equivalent body forces. One is acting in 1, so along X. The other one is acting along Z. How they are made? Well, this is containing the discontinuity field, so the amount of slip over the fault plane, times mu, times 2 deltas, and we will see now, times a partial derivative of a delta with an arm in Z. Because this is telling you, okay, put an arm in Z. Okay. We have nothing along the y direction, nothing, because remember, 1 free, free 1. Then we have a force into Z that is related to the slip on the fault, times mu, times some deltas here, and this partial derivative. Everything has to be integrated over the fault. So these are two variables along x and y. Now let's imagine to perform this integration, and the average will be this amount of slip, mu, and what? What do we have here? Wait a second. It's a delta into the z direction with an r in the z direction. What is this? Okay, it's a term related to the derivative of a slip on the fault. It's here along x. So we have a slip field on the fault pointing along x, and we have to compute its derivative times mu times a force along z. Okay, it's not that exciting until now, but you can see that when you assume that ni and u are given in some directions, all the terms here become very, very, very simple, because only mu is left, and it's saving just some components of all that mess. Okay? Let's give a look to them. Now we have two body forces. Let's give a look to them. Okay. The first one, remember, this one. Okay? But
The symbol that this symbol represents,
which one?
eta and this delta into that symbol with 3, that thing, yes.
you know, to make it better. That's the fold. Now, remember that 1, 2, 3 could be x, y, z, or something like that. The symbol there, etas, are nothing else than the coordinates of the fold. So it could be 1, 2, and z, and 3.
Okay.
But eta is running on the fold, pointing into different directions.
Okay.
And the integral now has to be taken just along 1 and 2, because ni is z and u is 1. Okay?
Yeah.
Let's give a look to the first one. Okay. The first one, so F1, is representing a set of single couples distributed over the fold. And they are pointing along 1, but with an arm along z. That's by definition. Now it's a set of couples. Definitely, their arm that is making along z and their force that are pointing in 1 and 3, all of them have a net moment along y. Remember, x and z. Okay? Remember that a moment is acting on a perpendicular when you have a couple of forces. Force, okay? Rotation is occurring in the perpendicular plane. So the first one is a distribution over the fold of a set of single couples. All of them are pointing along 1, and the arm is along z. So you have to imagine that the arm is across the fold. Okay? What is their strength? Well, it depends on mu and on the slip, amount of slip. So they will be larger where the slip is larger. Okay? Question. What if we compute the total resultant and the total moment of this set of equivalent forces? Well, with some algebra, you can compute the integral over the volume of this force here. You can demonstrate that it is proportional to this, and it is 0. Well, of course. We started from something whose total resultant is 0. If you compute the total moment, and it's messy, just to tell you that if you compute the total moment of this set of forces that are acting 1, an arm, and here, okay, it has a total moment. It's positive, and it is mu times the average slip times A. Oh, it's plus m0. Okay, good. So the first equivalent force is something that we are waiting for. Because if you look from the side of a fold, let's imagine the fold is here and we look from this side, okay? So this is, let's put Z for simplicity, and X. We have a set of couples like that, okay? Whose amplitude is varying according to the amount of slip, okay? We have a total moment that is coming out and it is plus m0. Total resultant is 0. Okay, if you think about it, this is intuitive. It's a set of couples, okay? With a total moment. Now, let's give a look to the second one. Well, the second one is a little bit more tricky because it is that one. Now, what we have to compute is to compute the derivative in x of a slip distribution times mu, and then we multiply by deltas that are pointing in z. Okay. Let's imagine that the slip distribution is like that. 0, something, 0. If you compute the derivative of this function here, you have this. And if you fill it with forces, you have this. Oh. That's funny. We were not waiting for something like that. But, okay, there it is. The total force is 0. The total moment is not 0, is minus and 0. And it is pointing on the other side of y. So, just to sum up, if you put everything together, you have a total resultant that is null, a total moment that is null, and we have a set, 2 sets of equivalent forces. Are we happy with this? No. Well, at least I'm not happy. You know why? Because the dream would be to have another set of couples, like this one maybe. But not like that. I would prefer a lot a set of couples, maybe in Z, with the arm, in this case here, along X, and something like that, so that when I join them, I have a set of double couples. Oh, that would be great. So that when we squeeze everything together, and we are far from the source, and we have just one body force, it's a double couple. That would be great, right? Don't worry, we can be happy, because this force here can be rewritten exactly as we wish, with some math, of course. Because actually, the force equivalence to a given fold slip, remember this representation here, can be written in many, many ways. That's strange. Because the representation theorem actually is allowing you, when the fault is extended, to use it in many different fashions. This is my preferred. For example, that's the general expression of shear dislocation, okay? Okay, look, let's give a look to this one. You can write it, in this case, 1-3, remember, 1-3 now, okay? 1-3, like that. And we can write every term here, the derivative, the spatial derivative, as a limit of an incremental ratio. Good. So we can write this one like that, and this one like that. Oh, that's nice. Because now look what we have here. 1 and 3, and 3 and 1. Now we have a set of double couples. Because the first one is like the first, and the second one is like that. Good. I love this one. So that we can imagine that if you overpose these two, now we have a set of double couples. This is my preferred version. So now what we do have here is a set of double couples. Okay? They are pointing in Z, X, Y, because the displacement is in X and is in Z. So we have a beautiful set of double couples. The orientation is XZ. It's due to the geometry. And that amplitude is related to the distribution of slip. So where the slip is maximum, the double couple will be larger, and so on. The total resultant is 0, the total moment is 0. Everything is fine. Now, is that the end of the story? No. Do you want to see another fashion to write it? Okay, we have another one. There are many. For example, you can write this one like that. And the representation will be like that. So the first one is still the same, but the third one is different. What is my message to you is that the representation theorem, when the source is extended, so it's not a point, can be used to write the equivalent body forces in many fashions. You have seen 3. The first, classical. The second, the most useful to me, because it's the most useful to be implemented, or a third. So you could say, you should say, what? We spent more than 2 hours in this theorem, and it's giving us different representations. Yes, but the point is important here. When the source is extended, this expression here can be rewritten in many different ways. It's up to you to decide which one is the most useful. In my opinion, this. Because actually you can imagine as a set of subsources. All of them is a double couple with different strength. And the orientation is resembling me and you, 1 and 3. But you can use different representations. But when you go to the point source approximation, all the possible versions are going and converging to just one expression. And it is this. So, final message. Once you make the last step and you assume a point source and you perform the integral, all the different versions that you have seen of equivalent body forces are getting out in this. Because if you do perform the integral here, what you're left is with these 2 forces here. What is that? Okay, this is a couple in Z, this is a couple in X. And so, the end is that we have just one. We have a couple in Z, a couple in X, and the strength is given by plus M0 minus M0. And there you go. So actually the representation theorem that I was showing to you with the abstract was saying, okay, the representation theorem for a point source will be a double couple for pure shear dislocation. And that's the end of the story. And that is the most adopted model of a source. And I hope you do feel now what is the physical meaning of M0. But I was writing to you since the first lecture as this. Now you do understand all the terms, because mu is coming from shear dislocation. A is coming out from the integral of the fault, and this is the average of slip after integration. And it is the moment of each of the couples 2. But together, they do represent a shear dislocation on a fault. And M0 is the moment of this and of this, plus, minus. Why it's called seismic moment? Well, it's representing a seismic source, and it is a moment. Force, area, 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 force times displacement. So, it's Newton times meters. So what I'm trying to say is that the information that was about the fault at the beginning, you remember the fault was here, slip was there, the knee was Z, it's then represented by this. And that's why it's 1, 3, so it's 1, 3, forcing 1, arming 3, and 3, 1, forcing 3, arming 1, it's symmetric. Plus M0 minus M0, in the principal axis, everything is plus M0, 0 minus M0. And the axes are this, this is T, this is P, and this is B. Okay. And that's what the final slide for this tremendous set of lectures, set of slides, is this one. And we will give a look to it. In the next lectures, we are going to deeply use this theorem in many ways. On the next lecture, first, we will try to define Green's function, because we have used it, but we have not defined it. Okay. Then,
the solution?
yes, we will do it just for simple models, but it will be a mess. Okay, but a useful mess. Second, we are going to use the Green's function that we are going to find plus this approximation here of a double couple to look for the radiation from a seismic source when it is a point. And we will go for focal mechanisms, because we need now the Green's function. And we will use the axis of the source. Remember one thing. When you are at the source, traction is something that is pulling you if you are the source, right? P will be a compression for me that I am at the source. So minus plus, okay? When you are the receiver, 2 lectures, the wave that is coming from the source that is pushing me, okay? Compression, stellar reflection, do you remember sound waves? What is pushing me will be positive for me, but for the source, what is pushing me is attraction. This will be a plus for a receiver, but it will be attraction for the source. So just a warning, because for focal mechanisms, we will have to take care about this double personality between the source and the receiver. Okay. What we have left is the discussion of this final slide that is a sort of a summary. Now, let's start from the source. The source in the specific case was a fault, like this, with normal knee in Z, okay? And U like that. If you want to describe it in terms of a strike, dip, and rake, what we have to use is, okay, strike 0 means, okay, the strike of a fault is along the north. Let's imagine the north is there. Fine. What about the dip? Oh, dip is 0 in this case. What about the rake? Okay, is 0 because it's going towards X. So you take these 3 angles, strike, dip, and rake. They are all 0. Nice. It's geometry. With those definitions, U and knee are like that. U is the average of the slip, and it is along X. Knee is just along Z. What does it mean? Well, the TBP, now they are defined as I've shown to you. So XZ, so they are diagonal, like in that case there. And B is in Y. Good. Well, you can write them now using the other set of coordinates in terms of MPQ. So the density of a moment tensor, for example, is mu times this average, and it is 1, 3, 3, 1. Sorry for that, because it's me and you. And so the moment tensor, MPQ, oh, I was deleting it, for this source is very simple. But wait a second, because if you use TBP, it's diagonal. Plus M0, 0, minus M0. Okay? 1, 3, 3, 1, 1, 1, 0, 3, 3. And so you have a double couple that in this case here is just, I don't have it, but let's imagine, okay? You have one couple and another couple here. So you can throw away the fault and leave just a double couple, 1, 3, 3, 1. And if you refer to the principal axis here, it's just that. So all this tremendous mess to describe this. So remember, the representation theorem started a long time ago. Now, if you give a look again to the abstract, for displacement dislocation fault, pure shear dislocation, the double couple is an exact equivalent body force for a point source. Otherwise, every time that you relax one of the conditions, you have to make some step backwards. Okay? Now, since we have 10 minutes left, what we can do is to start, because we're a little bit late, this beautiful lecture about the Green's function. Okay, don't look at this. Don't look at this, and you will get scared. But let me use just these final minutes to recall you what is a Green's function. Now, Green's function, for very simple, how to say, differential operators that have to be linear, can be defined as the inhomogeneous solution of a differential equation when the inhomogeneous term is a delta. Just to wake you up, it's like this in this row. With globes, it's working different, so it's not a delta, but it's something different. Okay. So if I clap my hands here and you record with a mic, with a microphone there, you will get a recording. That's the Green's function with me at this point here and the mic at that point there. We have not demonstrated, but I can tell you that if you put myself there with the balloon, and if you put the mic here, the recording will be the same. It's called reciprocity. By the way, clapping hands, you can record the Green's function this way. But it's not the simplest problem. For example, the simplest problem that we can imagine is a one-dimensional problem. What is the simplest that we can guess? Oh yeah. Hooke's law. Okay. We have a mass here, minus kx, Newton, Sir Robert, and so now we have and we did it.
Yes.
And the solution is
Circular. Sinusoidal.
where amplitude and phi, amplitude and phase, are decided by initial conditions. What does it mean? Okay, displacement and velocity. Zero initial displacement, some velocity, and we can write it. Zero initial velocity, some displacement, and we can write it. Then you should say, wait a second, it's going to stop in some minutes. Because my hands, because the air. So please do remember that here we have, in many cases, to add something related to the decay in time. It's a damped harmonic oscillator. And so, you should say, wait a second, that's no more valid. Let's add this, friction. But it still equals 0. So it's still a it's linear.
Homogeneous.
Yes, it's linear, beautiful system, but it's homogeneous. So our L of x here, actually it's an L of t, is, okay, double, let's use t, something plus something plus of something. This is our differential operator. It's linear, self-adjoint, it's beautiful, but we solve it when it is homogeneous. Why it's called in this way? Because homogeneous systems are like algebraic systems, an equation equal to 0. And in linear algebra terminology, you can imagine something like that. It's called homogeneous system. Now, when it is not 0, it's called inhomogeneous. Okay, when it's not 0, it's not homogeneous. And we have now a problem. It's an inhomogeneous problem. And it's not easy. It's me forcing it. Whatever I'm doing here, I'm forcing. We solved it. We used a trick. Because I was lazy, if you remember. So I told you, okay, let's consider a very simple external force, and we have chosen a specific. And we said, okay, come on. It's a beautiful harmonic function. It's me doing something like that. Very fast or very slowly. Or at its period. Wow, resonance. And we solved it with some tricks. So we discovered that the general solution is made by the solution of the homogeneous plus a particular solution of the inhomogeneous. Good. But in general, we don't know the answer to this problem. If someone else is coming here and making strange things, that's f of t. How to solve it? No. George Green is saying, don't worry. Solve it for this, and I will tell you the answer. So, Green's function is the solution of a problem when the forcing, the inhomogeneous term, is a delta. Is a delta at some time or in some place. Okay? The solution to this specific problem, battery is gone? No. When we have a solution in X, the receiver, and when the source is in S, it's called Green's function. Thank you, Sir Green, because once we know it, we can write the solution to the general problem. Why? Because we use its linearity, so this should be an integral here, as I told you. You can multiply the last equation by f on both sides. This is linear, so you can take out L. This is, by definition of a delta, is nothing other than f, computed in x, but then it is this one. This is out. Okay, so looking at this, now we have a solution. It's actually the convolution of the Green's function times the generic function, the Green's function. So usually Green's function is used to find the solution of inhomogeneous problems. And we have used that definition for our specific problem. What was that? Okay, let's use the representation theorem, reciprocity theorem, using as one of the solutions something that we know. And we defined, oh, wait a second, maybe we can just discuss it. I was adding these slides here 1 year ago because maybe they were, yes, just one. Remember that Green's function is very, in a positive way, pervasive. You can find it everywhere. Every time that you have a linear problem, you can find it. For example, linear systems. By definition, linear system is something that if the input is made by, okay, x1 and x2 with some constants multiplied, okay, if the solution to x1 is y1 and x2 to y2, well, the solution to both combined will be a linear combination. That's the definition of a linear system. So it's conserving multiplication by scalars, and it's conserving addition properties. Very easy, okay? So if you enter with x1, you know it's giving out y1. If you're entering with x2, you know that you enter with y2. If you enter with ax1 plus bx2, then the output will be a plus b. Definition of linear system. Okay? And it's time invariant. Otherwise, we
Do the output constant AB are restricted to be the same as the
yes, if it is linear, it is. Yes. And so, in general, when you have a linear system, and let's imagine that, for example, it's a function of time, like this. Okay, so it's an L of t. Okay. For a generic input, x of t, you can always write x of t. Let's imagine x of t is a function here, and let's imagine to write x of t, that's your input, okay? You can always write x of t as a sort of a convolution of the values of x with delta. Okay, and you make the delta run. Okay, let's enter with this. If you enter with this and the system is linear, look, you can consider these ones as the multiplicators that are describing the function x at every time. So we are numbers multiplying deltas. Now let's enter with this here. It's linear. What does it mean? It's conserving multiplication by scalars. And the solution for delta is h. It's the Green's function. Actually, it's called the impulse response. Okay,
Impulse?
impulse response. The response
Oh,
to
impulsive.
impulse. Sorry, I'm Italian English, spaghetti English. So
My own
it's-
English is not good.
okay, impulse. Okay, that's better. Now, the solution when you enter with delta, you will get out with h. So this input will cause that output. But this is nothing else than the convolution of the input times the impulse response. And that's the general solution. And everything is due to linearity. So the Green's function is everywhere, every time when we have a linear problem. Could be in time, filtering. Could be in space, pictures. Could be in time and space and direction. It's our problem. Because we have to solve the elastodynamic Green's function. So, what to say here is that that's the definition for a generic linear differential operator. Its definition for time domain systems. With this definition, it's very important when you apply the Fourier transform, because the convolution product will become algebraic product of Fourier transforms. That's easy. It's beautiful. And the Fourier transform of the impulse response is called the transfer function. Okay. Now what we are left with? This. Oh my. This is what we have used inside the representation theorem. So we have a linear differential operator, the equations of elastic motion. Beautiful. Acceleration, spatial derivative of strains, and when it's not homogeneous, but it is a delta in time, space, and direction, the solution is the Green's function. But we have to agree, that's the definition, it's not the solution.
Mm-hmm.
And we will start from what? Solving the simplest problem that we can imagine in elastodynamics. It's this. But it's nice. Because what do we have? We have a beautiful homogeneous space with a delta in time, some time, a delta in space somewhere, and we will start with an isotropic problem. Okay? Purely isotropic. It's not what we need, but it's simpler. We can train there. This problem, so it's a delta in space and time, but it's, for example, a gentle explosion or an implosion. Now we know it can be related with M11, M22, M33. So maybe we can use it, for example, for applied geophysics. This is easy. This is easier, you know why? Because we don't have directions of a force. As I've shown to you, when you apply a force in one direction, the other, the recordings are different. So we need to explain that. And that part will contain the radiation pattern. In this case here, we are not waiting for radiation pattern. We are waiting for radiation isotropic. So it's much more symmetric, much easier, and can be solved just using simple maths. We will start from that, but then we will have to solve the Green's function. But it's too late. So we will start next one with this. Next Wednesday. Okay? Okay. Again, this part of the theory is, in all the details, explained in the Akin and Richards. But a simplified version is also on Steinway's session. Again, for my wishes of your knowledge, it's enough that we logically understand what we do together. So if you want to write pages of algebra, you're totally free to do that. But between us, what is needed is what we're going to discuss together. Okay? Have you started the course with Alessandra?
Yeah, already.
Okay. Okay.
Four lectures.
Okay. Actually, the next, what we're going to hopefully discuss on web about the Green's function is containing part of the theory that can be used also for a GPS recording of an earthquake. But of course, her course is much more wider. So.
You stopped recording?